Okay. Well, we've been doing particle stuff so far. Now we're getting into rigid body things. So remember, for rigid bodies, we have the equations, add up all the forces, F net, I guess. It has to add up to 0. This gives two equations in 2D and 3 in 3D. And then we have MA net. In general, that's a vector, is equal to 0. That's one equation in 2D because there's only one axis of rotation in a plane, you know. And 3 in 3D. And that comes out to 3 total equations in 2D and 6 total equations in 3D. Okay, so that's going to be how we do statics for the rest of this class. So I'm going to start by defining what a moment is, give you some organizational stuff that helps you keep it straight. So a moment. In physics, they sometimes call it a torque, but in engineering, a torque is kind of a specific combination of moments. So we're going to call it a moment. People call it a moment because it's shorter. But really, it's the moment of a force about a point. And obviously, the force that you're dealing with matters in what the moment is. The point that you're calculating it about also matters. So whisper that stuff to yourself whenever you say moment. By the way, do you know what the word moment really means? It really is just a mathematical term that means the integral of something times a position dimension. So that's what it comes from. That's why you also have moments of inertia, moments, you'll hear moments come up from time to time. It's really just a mathematical term. But people tend to just call this the moment because it's the one that comes up the most. Okay, so if you have an object, that's your random object. And you have a force applied at, so this point is P, okay? And just some arbitrary force vector that I'll call F. And then over here you have your about point A. Draw the vector that goes from A to P. And we'll call that vector rho, the Greek letter rho, like a script EP. Then the moment about A produced by this force F is equal to rho cross F. So let me label some of these things. So A in this is the about point. So that's the point that you're calculating the moment about. Remember I mentioned last time that in statics, that you can choose that point A to be anything you want. It's just for that single body, you have to keep it the same. Obviously, you can't choose a new about point for every force, or you'd choose your about point at the location of the force and every moment would be 0. That doesn't do anything, you know. So once you choose your about point, you have to keep it the same. When you get to dynamics, you have to remember that that's not the general rule, and there are only specific places you can use an about point. But for statics, you can do anything. Oh, why is that? I hear you all asking. So why in dynamics are there only 2 points per body, at most 2 points that you can choose as an about point, but in statics you can use anything you want, you know? The answer is the simplified form of the moment equation in dynamics comes from certain velocities and angular velocities being 0, okay? So if you choose your about point at the center of mass or at a fixed point, you have certain velocities and angular velocities that are 0, and it simplifies the equations. In statics, all our angular velocities are 0, and all of our angular, well, if you choose a coordinate system in a certain way, all your velocities are 0 too. It's statics, you know, everything's at rest. And so that means you can treat every point as if it's fixed in space, like every point as if it was a hinge. That's why it works that way. Okay, so the meanings of these things. A is the about point. P is the point where the force is applied. That rho vector is the vector 2p from A. And notice that you can always calculate this. If you have the coordinates of P and A, you can always calculate this as P minus A. Okay, so this is how you calculate the moment, and these are the meanings of those points. Intuitively, you can always think of the meaning of the moment in terms of like a wrench turning a bolt. So this would be your about point. This would be the point where the force is applied. There's the force vector. The rho vector goes from A to P. So that's the rho vector. And if you're trying to turn this, if you know you can apply a force with a magnitude F, and you're trying to turn this bolt, you know from experience that you want to apply that force way out on the end of this wrench, you know. If you apply that same force at the middle of the wrench, it's less likely to make it turn. And if you apply that force at like where that force points straight through the about point, then you might rip the bolt off the wall, but you'll never make it turn. It doesn't tend to turn at all without a moment arm rho. Okay. Also, what if you applied that force F? What if you applied that force F straight this way, you know? It's the same force. The distance between P and A is still the same, but you know, like pushing on this, it's not going to turn that bolt, right? What matters is the perpendicular distance of this thing. It's the component of this P minus A vector that's perpendicular to F, right? That's what the cross product does in this equation. The cross product makes sure that you're not taking into account anything that's parallel to F. Okay. I recommend this sort of bookkeeping tool. So you write out this table with a column for rho, a column for F, and a column for the moment. And I'm just giving you some arbitrary values. So let's say that the rho vector is 5, negative 2, 0. The force vector is 0, 500, 0. This is a rho vector and a force that are in the xy plane. So let's think about what this looks like. So if that rho vector is 5, negative 2, 0, the rho vector is something like that. So you can think of the force where the point where the point where the force is applied there, the about point here. The force is 0, 500, 0, so that force is this. The cross product, since this is in the xy plane, you can sort of forget about that 0. And what you get for the moment is only going to be in the z direction, and you're going to get 5 times 500 minus negative 2 times 0. And so you're going to get 2,500 for the z component. And so with this table then, for a single rigid body, you would enter one row of values for each force that's applied. Okay, so then you'd have that force, that force. You'd go, if this body had 10 different forces on it, you'd have 10 rows, okay? And once you're done filling out this table, add these all up, and those are all your forces for Newton's second law, and add these all up, and these are all your moments for the moment equation. Okay, so it's just a nice way to have everything right in front of you. If you find an error, you have all the information you need to go back and correct it, you know. I think you'll find that that works nicely. The right-hand rule as a tool for moments. So think only about the single force you're considering. Just one by one, think about one force. And then ask yourself, would that force rotate That's a bad wording, I'm sorry. I know you can't do this on your paper. Curl your fingers in the direction that force would make the body rotate. Around the about point. Then your thumb is in the direction of the moment vector. Okay, so let me draw this. So if you have, let's think about the case we just did with the bolt. So this is the about point. This is the force vector. If you don't worry about any other forces except F, that would tend to make this rotate. So think about this, the hinge where this can rotate is the about point A. Is this force F going to make it rotate clockwise or counterclockwise? Counterclockwise, yep. So let's see, I'm going to try to draw this. One, two, three. Okay, so that's supposed to be like your thumb coming out. So curl your fingers in the direction of the moment. Your thumb points in the direction of the moment vector. Okay, so if this was in the XY plane, then the z-axis is coming out of the page, and so this force would have a positive z component of that moment. Okay? All right, so what about three-dimensional moments? In 2D, it's pretty easy to picture this. What about in 3D? Yeah, you can. I mean, I'd recommend just using the, just use the cross product. But you can think about things this way because, so let's say that you have, let me draw a coordinate system. So let's say this is the x-axis, the y-axis, and the z-axis. And let's say, so the body that we're looking at, let's say it's a plate like this. Okay. So you can see the x-axis goes down sort of the middle. And let's say that our our force, is applied here. And let's say that, so you have a force vector, it has various components. Let's break the components, break it up into its components. So let's say we have one force component that way and one force component that way. Now you can just think about the cross product thing component by component. Okay, so, and then you just add up the moments at the end. So yes, you can do it as if the separate components of each force are just their own forces. So which way would this component make it? I didn't give an about point. Let's put an about point. Let's put it here for now. Okay, so there's the about point in the corner. Okay, so which way would the upward force make it rotate around that hinge? You can see it would make it rotate this way about z. Okay, so the component of your moment is going to be this way. So you're going to have one component in the positive z direction, and then this one is going to make it rotate like this. You see that? Mm-hmm. And so that is in the positive y direction. So you're going to have another component of your moment in the positive y direction. So yeah, you can think about it intuitively, component by component. Okay? Okay, so if you break up your force into components, you can use this right-hand rule on each component, and then just add up the results. Well, this is the way that, you know, people used to calculate moments when using cross products was a little tedious, you know. That's a way you can do all of these problems. I guess I'll probably show you at least one simple problem doing it this way. But I think you're going to see that that it really is a lot easier and cleaner to just use the cross product to calculate moments. Okay, for 2D, so notice, we're going to do a lot of 2D problems. And for 2D problems in the XY plane, moments are always parallel to the z-axis. They only have z components. And that's because if you calculate the moment of a row vector like this and a force vector like this, to calculate the x component, cross those out, and it's this times this minus this times this. Okay, notice that both of those are multiplied by a 0. And so you get 0 for x. Then cross out the y components. It's the negative of this times this minus this times this. Again, those are 0. And then the last one, cross this out. This times this minus this times this. That's not 0. So you get rho x fy minus rho y fx. Okay. All right, let's do an example. So let's say our about point is here. And we have a 20,000 Newton force up and a 10,000 Newton force to the right. And for dimensions, let's say this is 0.5 meters and this is 2 meters. Calculate the net moment about A. Okay, well, I'm going to write out this table. So rho, force, moment. And we're going to have 2 columns. So the first one, I'm going to do the 20,000 Newton force. Okay, so the rho vector, we're talking about the vector that goes from the about point to where that force is applied. And I'm just using a standard coordinate system like this. Okay, so what's that rho vector? It's going to be +2 in the x direction and 0 in the y direction. We're looking at this vector here. Always, if you want, you can always calculate the coordinates of A in some coordinate system, the coordinates of P in the same coordinate system, and just subtract. Okay, so your rho vector is 2, 0, 0. The force vector is in the positive y direction, so this is 0, 20,000, 0. And the cross product is, so you get 0 for x, 0 for y, and then positive 40,000 for z. Bless you. Okay, so that's the first one. There's another force. So now we'll do the 10,000 Newton force. So what's the rho vector for the 10,000 Newton force that's acting here?
2, -5.
Yep, 2, -0.5, yeah. So 2, -0.5, 0. Everybody see that? The force vector is positive 10,000, 0, 0. And the moment you get is 0 for x, 0 for y, and then 2 times 0 minus -5 times 10,000 gives you positive 5,000. And so the moment, the net moment, you get from summing those. And so MA net is equal to 0, 0, 45,000. And the units here are, I did forces in newtons, distances in meters. So this is Newton meters, the SI units for moments. I want you to notice that if you're doing 2D problems, this is what it means, right? A moment is always a vector. If you're doing 2D problems, it's always a vector that's parallel to the z-axis. But to save, pen strokes or whatever, you could always write this like this, and it conveys the same information. You just need to remember that you're talking about moment vectors. So you could write this as just 2, 0. Write this as 0, 20,000. The cross product is this times this minus this times this. So you get 40,000 here. You could write this, then write this one as 2, negative 0.5. The force vector is 10,000, 0. Cross product is this minus this. You get 5,000. All you have to do then is just remember that what you have here are z components. Okay. So it conveys the same amount of information with a little less writing. Just don't forget what that means. Okay. Anybody have any questions about that calculation? Okay, let's do one in 3D, and you'll see, this approach and this table and everything works exactly as well in 2D as 3D. Okay, so let's say we have a plate. And there's a cable attached to the center of the plate. And it connects to the wall right above that corner. This distance is 1 meter. And we're going to imagine that this thing has the same lengths in both directions. So that's 2 meters, and that's 2 meters. And we're going to assume that that cable tension is 10,000 newtons. What's the moment produced by the cable? About the point A. And I'm going to use this point as A. Okay, I have to tell you what coordinate system I'm using. So let's use the x-axis going this way, the y-axis this way, and the z-axis then has to go this way. Okay, so for this one, let's just figure out the coordinates of the point P and the coordinates of the about point. So this is the about point A over here. Okay, and we're just going to do the subtraction to get that row vector. Everyone with me on that? Okay, so we'll name this point P. So P is the origin that I drew. So 0, 0, 0. The point A, let's come up with the coordinates for that. So that's going to be, if our P is exactly at the center of this square, where do you have to go along the x-axis?
-1.
Yep, -1. Everybody see that? Okay, so we have -1. And then where do you have to go along the y-axis? 0, exactly. And then what about the z-axis?
-1.
+1, yep. And so together this row vector is P minus A and so that's 1, 0, -1. And now we have to figure out the components of that force vector. Okay, well that's going to be a little more work. But you've done problems like this on the vector review stuff. So what we're trying to do is come up with the unit vector. I'm going to name this point too. I'll call this B. Okay. So what we want is a unit vector that goes from P to B. Right? And then we're going to multiply it by the magnitude of that force, which is 10,000. Okay? So, well, let's come up with the coordinates of B. So to get to B, you have to go -1 in the x direction, or 1 in the negative x direction. Then you have to go +1 in the y direction. And then you have to go 1 in the positive z direction. So a vector in the direction from P to B, or to B from P, I'll call it U, is equal to B minus P, which is -1, 1, 1, minus P is 0 in this case. That's not a unit vector, though. And so to calculate the unit vector, you can just use the unit v command on a calculator. Or, figure out that the magnitude is 1 squared plus 1 squared plus 1 squared square root. So this is square root of 3. And so the unit vector in the direction of U is -1 over root 3, +1 over root 3, +1 over root 3. Which is -0.577, +0.577, +0.577. And now that we have the unit vector in the direction of that force, we multiply the unit vector by the magnitude of the force, which is 10,000. That was given in the problem. So this force vector is 10,000 times this, which is -5770, +5770, +5770. And now I'm going to write out the row of the table for this. So we have the row vector, the force vector, the moment vector. We're doing the cable force. So the row vector was 1, 0, -1. the force vector was negative 5770, positive 5770, positive 5770. And then cross product, it's easiest to do that with your calculator, but you get, so for the x component, cross that out, it's this times this, minus this times this, so that's 5770. Whoops. Okay, so 5770 for the x component. For the y component, cross out the middle ones. It's 1 times 5770 minus negative 1 times negative 5770. So that gave us a negative 5770, and then because y is the messed up one always, this comes out to be positive. No, it doesn't, because I didn't subtract. So we got 5770 minus 5770, so that comes out to be 0. That's good. I'm just trying to make sure everyone's paying attention. Okay, so 0. And then z, cross these out. And then it's this times this minus this times this. So this one is positive 5770. But you can see I'm a good candidate for just typing that into my calculator. Any questions about that? So this approach works exactly the same for 2D and 3D. That's a nice thing about it. Let's do a statics problem, just a 2D simple statics problem.
Can we look at that vector in the diagram real quick?
Yeah. Up here?
Yes.
So the moment vector in the diagram. Okay, so let's think about it. I said you don't have to do it by cross product. You can do it by breaking up the force into components, you know? Let's think about it that way for a second, okay? So this cable force component has, what does it have? It has a x component that way, right? It has a y component that way, and then a z component that way. So it had 3 components, right? Yeah. So one by one, let's think about the components of that moment vector and compare it to our answers, okay? So forget about that cable being there now. Just think about the components. The first component is an x component, you know, in the negative direction, okay? And forget all the other forces for now. The only things you care about are the force going in negative x and the about point that it rotates around. Okay. Well, what was that component? 5770, right? In the negative x direction, the force component. So you have a force of 5770 going that way. You have a moment arm of 1 meter, okay? That would make it rotate like this. So we know that that x component of that vector is gonna be about y, right?
Yep.
And,
It's gonna come out.
oh yeah, well, okay, so that one is going to produce a y component of 5770 in the positive y direction, okay? That's gonna be canceled out by another one because we know that has to come out to 0 later. Then the y component, that's 5770 up. So what kind of moment would that create around this?
Positive z.
yeah, positive Z, and that's a force of 5770, a moment arm of 1 meter, so you can calculate that component. And then last one, Z is going to, so 5770 this way is going to rotate this way. That's a negative Y moment. 5770 cancels the original 5770. So you can get all these same numbers by just thinking about it component by component. But it's, I mean, it's just way more tedious than plugging it into your calculator, you know. Okay, I have to do this example problem so I can assign you more problems. So let's just do this. Okay, so let's say we have a, I'm going to do a super simple one. So let's say we have a board like this. It has a weight force, say, of 200 newtons. And a force down here of 100 newtons. No, don't do that. Those will cancel. Let's do 300 newtons. And then we have this unknown force vector here. That's the reaction force applied to the object by the hinge or whatever, okay? We'll talk about the forces the joints produce next. Okay, so if this is in static equilibrium, bless you, what is the force vector R? Okay, I'm going to put the about point where that force R is. It doesn't matter where you put it though. And I have to give dimensions. Let's use the same dimensions we just used. So I'll call this 2 meters and this 0.5 meter. And this is our about point A. Okay, so rho, force, moment. Let's do the 200 Newton force first. So to get from A to P, where this 200 Newton force is applied, you go 1 meter in the positive x direction, negative 0.25 meters in the y direction. The force vector is 0, negative 200. And so the moment is 1 times negative 200 minus these two, which is 0. So you get negative 200 for the answer there. Remember, that's a z component. Okay, I'm just sort of doing a shorthand of it. Next, the 300 Newton force. To get from A to where this force is applied, you go 2, negative 0.5. And that force vector is 0, positive 300. So you get an answer of positive 600. There's one more force. That's this reaction force that just has, we'll call those components Rx and Ry. Oh, this isn't going to work. Hold on. I have to add something else here. So why isn't this going to work? I mean, if you put a board here and had a hinge here and apply these forces, it can't be in static equilibrium. It's going to fall down. So let's put a cable here. Sorry, pretend I did this before. Okay, now it can be in static equilibrium. That cable's going to hold it in place, right? Okay, so what's the row vector for this force R? The vector from A to where that force is applied? 0, yep. So we have 0 for the row vector. We have Rx, Ry for the force. Cross product says this is 0. I'm sorry, I'm going a little over. This is almost done. Okay, now we need the cable force. So the cable force is applied there. The row vector is 2, 0, 0. Or 2, 0 if we're just using the two components. The force vector is 0t. Cross product then is 2t. And now we're almost done. Add these up, set it equal to 0 for Newton's second law. Add these up, set them equal to 0 for the moment equation. So Newton's second law says 0, negative 200, plus 0, 300, plus Rx, Ry, plus 0t is equal to zeros. And the moment equation, I'm going to call that rotational Newton's second law, Rn2L. So that's negative 200 plus 600 plus 0 plus 2t equals 0. So this tells us that t is equal to what did I do here? Oh, God dang it.
Pushing up.
Yeah, it's pushing up. You can't get a cable to push.
Down.
So, okay, hold on.
It could be
Okay, wait, no. What?
The cable could be going down. What if you double the weight?
Yeah, what if it's a bar? No, let's change this force. I'm sorry, just change this to 50. Okay, 50. You know what the problem is? Pearl Jam concert. Okay. Okay, now it'll work. Okay, so pretend I never said 300, I said 50. Okay, and this is 100 now. And this is 50. And this is 100. I think I got everything there. Okay, so now 2t is equal to 100. T is equal to 50 newtons. Plug that back into Newton's second law. Rx is equal to 0. Ry, so let's see, we have negative 200 plus 50 plus Ry plus 50 is equal to 0. So Ry is equal to 100. Okay, well, maybe I'll edit that video. And then the class won't be too long either if I take out the 5 minutes I screwed up. Anybody have any questions about that? Okay, well, that is the procedure. You can presume that the questions you'll be given will work. And okay, that's all.